otomobil, yani araba satıcıları, banka şubeleri.
Hi.
Yani orada bir şey servisi veriyor.
Hi hocam, hello. Can we start?
Whenever you want.
Okay. Hello everyone. Welcome to the webinar organized by the collaboration of Civil Engineering Sustainability Team and ISS Meteo Local Community. Today, dear Çağla, Meral, AKGÜL, we will make a presentation on life cycle assessment of the construction material for us. Now, I am giving the floor to our beloved teacher.
Hi, thank you so much for inviting me. And I am very surprised to hear that today is the Environment Day. So I hope background is suitable for this. And today I want to talk about something that probably you all thought about, life cycle assessment. So when you look at something, most of you wonder, of course, maybe the cost, the performance, mechanical performance, as civil engineers, I mean. But we start to also think about how green that product is or that material is. So today I will talk about how to assess the environmental impact of a product or a service. It doesn't always have to be just a product, it can be a service too. So my computer, okay. So first, think of a role of materials in the environment. First, the direct impact on the environment is the first thing you think is manufacturing burden, which means consumption of energy and various emissions to the environment. Then the second thing is concentration in the environment. So most materials still eventually end up in landfills, and some materials are toxic. So these are direct influences of materials in the environment, the manufacturing burden, and then once the end of life comes, what is going to happen. And there are also indirect influences. In economics, this is referred as externality. So a consequence of an economic activity that is experienced by unrelated third parties. So what that means is a decision maker, the one that produces something, they don't bear all of the costs or reap all the gains from his action. So for example, think of a building. An architect designs a building, and then you basically a civil engineer constructs it. A contractor actually sells this particular building, but eventually we live in a building. And what happens is, for example, if the designers, if the engineers, if the contractor did not pay attention to energy performance of a building, the people who live in that particular building will have to pay higher energy bills, or they have to live in uncomfortable indoor environments. So what this means is an externality. So even though the engineer makes the decision, the contractor makes the decision, we, the occupants of the building, actually bear all the costs of that decision. And another thing is recyclability. For example, you buy a product, and then, for example, a milk bottle or a yogurt cup. You have to recycle it, but it's up to you to recycle it. It's not up to the company. So there are these indirect influences. So there are not just one player, but couple players. So this is also something that you should keep in mind. I want to show you a graph which represents a snap of materials consumed. Industrial minerals are by far the most consumed materials. Then comes non-renewable organics, such as fuels. And we also consume a lot of wood and agricultural material. Then we have some paper, and thankfully around after maybe 2010, the amount of paper we consume is slightly decreasing because we are passing to an mostly electronic system. And we also have some recycled materials, and we have these primary metals that we consume all the time. Industrial minerals, when I say industrial minerals, this includes cement. This includes concrete. So most of the materials that as civil engineers we use are actually included in this industrial minerals part. potash and phosphate for fertilizers, gypsum for drywall and plaster, fluorspar for acid, soda ash for glass and chemicals. And these are all included in the industrial minerals. Parka mı gidiyorsunuz? So they are going to a park. Kids are going to a park. Okay. And so I also want to show you the amount of construction materials consumed. So here what you see is, as civil engineers, we actually follow the economic trends very closely. Once there is an economic fluctuation, for example, a war, an economic depression, an oil crisis, for example, or a political crisis, construction sector is influenced right away. So that's why when you look at the consumption of construction materials, actually you can follow the economic trends of a country. Huh? So that's kind of nice and neat. And by far, construction materials are consumed much more than all other materials combined. I also want to show you another plot. This is renewable and non-renewable materials. Renewable materials include biomasses and wood products, and non-renewable materials include fuels, primary metals, industrial minerals, and construction materials. So these are non-renewable. As you can see, almost 90% are currently non-renewable. This trend is a little bit better today, and the ratio goes down to maybe 80% is non-renewable. I also want to show you a different version of looking at things. So using something and consuming something. So don't confuse these two terms into one another. Using is you use something, for example, here I use a teacup, a tea glass. So I use it, but it's okay. So I can reuse it. But here, I consumed my tea. So tea is gone now. So consumption and usage are slightly different. Consume means you basically completely lose it somehow. So think about materials that you use, but they are not consumed. For example, water. Water, you can reuse it. Or metals, you can actually recycle them without losing any quality. You melt them and basically you can reuse them very efficiently. So you don't lose any quality. Then, for example, you think of metals with alloying elements. When you recycle them, you lose a little bit of quality. Then think about paper or synthetics. When you recycle them, actually you're downgrading. So you lose quite a bit of quality. When you use recycled paper, it's not as high quality as these glossy white papers. Then think about cement. The cement, basically, once it hydrates, it changes the chemical composition of what you have. And reusing it is very difficult. Recycling it is very difficult. And then comes things that have very limited amount of reuse or almost completely consumed. For example, fuel. Once you burn your fuel, it's gone. You cannot recycle it, you cannot regain it. So these are consumed. So what you have is a decreasing quality and increasing loss. So this is something we don't want. We want materials that we can keep using efficiently if possible. So how much material do we use per day? So we use for one person, roughly speaking, 50 kilograms of materials and 2 kilos of metal, 3 kilos of minerals, 3 kilos of forestry products, 7 agriculture, 21 energy, 21 construction. So this adds up larger than 50%. And we have actually some outputs. And we have 2 kilos dissipated, 6 kilos as wastes, 19 kilos as air emissions, and we use 21 kilos. We only recycle 3 kilos. So this is an average for basic person. So how can we improve this? How can we actually enhance usability and we consume less. So how can this work? The first thing is you need to change human behavior. So how many of you, I don't know, prefers Starbucks paper cups? I'm sure many of you prefers Starbucks paper cups, but once you use it, it's gone, it's consumed. You have to recycle it, and for sure it will have a lower quality. If you use a glass like that, you can reuse it with no problem. So this is a simple example. Human behavior is very critical. You need to change patterns of your consumption. So you need to waste less. So for example, when you enter a car, when you set up your air conditioning, the temperature you set up, for example, outside is 30 Celsius. If you set your car to 18 Celsius, it will cool down to 18 Celsius and you will use a lot of energy. But if you set it to 25 Celsius, you will consume less energy. And you will be actually more comfortable because when you go out, you will go out to a 30 Celsius environment. So these simple things, changing human behavior is very critical. Once you change your patterns of consumption, you will waste less. And the second thing I can suggest is changing the rules. The number one thing you can do, what does changing the rules mean actually? The first thing is dematerialization. So if you can, design something or get something that has the same function but made out of less material. And the second thing is material substitution. So instead of toxic materials, use less harmful materials. Replace the ones that are critical for the environment with less critical ones. And the third option you can is waste mining. Waste mining, reuse and recycle. So find ways to make use of streams currently wasted, if possible. So these three rules, dematerialization, material substitution, and waste mining, together with enhanced human behavior, will significantly alter our waste generation. So overall, you want to make a change. All of us we all want to make a change. So how can we assess the impact of the change we make? So we are engineers, so we prefer numbers. So I did this. So can you quantify how green I become if I do this? So to do that, we use something called life cycle assessment. Basically, a compilation and evaluation of the inputs, outputs, and the potential environmental impacts of a product or a system throughout its life cycle is called life cycle assessment. It basically, to put it in simple terms, establishes an environmental profile of the system. And there are certain regulations, standards, how to actually calculate these life cycle assessments or conduct this life cycle assessment in a certain way. So here is a product's life cycle. M means material, E represents energy, and W represents waste. And arrows show material flow of product component. So everything starts, this is a very general outline of a life cycle. Everything starts with low material acquisition. Then we process the material, we manufacture and assemble if necessary, we use it and maintain it. Then eventually end of life comes and we basically choose one of different end of life scenarios and do as much recovery as we can. And then finally, you dispose it. And there are three things you can do. You can reuse it once the material or product comes to end of life and reuse it in a different system. For example, think of a building and you are demolishing a building and you have windows. You can actually take the windows and reuse them in a new building. So this is reuse. Then you can also do remanufacture. For example, you assume you have concrete, you crush it and use it as an aggregate for a different type of concrete. So this is remanufacture. Also, you can use it in material processing. For example, you have steel, you melt it, whoop, back, and this will be basically a closed loop recycle. So you can start it over. And there are also open loop recycles where you can use it in a different system, not on this particular system, but you can use it in a different system. By the way, you can put different types of borders in the system. So this is just a very general life cycle. You can have a wide range of different life cycles. When you think of building products, though, you start with resource extraction, then you manufacture, you construct it, and then people live in it. Once the economical or technical value of the building is completed, then you basically demolish it and recycle, reuse whatever is possible, and dispose whatever is not reusable or recyclable. So this is a very general life cycle of building products. So how are we going to determine the environmental impact of different options? So normally we have 4 stages in a life cycle assessment. Everything starts with goal and scope definition. Then we continue with inventory analysis. Then we actually do an impact assessment, and then we interpret all the results we got. So these are 4 main stages of life cycle assessment framework. So let's look at them a little bit more in detail. When I say goal and scope, what does that actually mean? This actually is there to answer several questions. The first question you need to ask is, what is the purpose of this LCA? Second is, who is the audience? What is the unit of analysis? Is it 1 meter cube of concrete, or is it 1 ton of concrete? What materials, processes, or products will be included in my system boundaries? Where are those boundaries? Are there any limitations? These have to be defined in goal and scope definition. Then we go to a second stage. This is the longest stage actually of the life cycle assessment. This is inventory analysis. I also will tell you maybe the Turkish version of this, envanter analizi. What do you need? What data do you need to assess the environmental impacts of that product? What assumptions are you making? Identify and quantify each of these consumption inputs and outputs, basically. Check energy inflows, material inflows, and releases. And then we need to do an impact assessment. Once we have our outputs, either there are different types of emissions to air, emissions to water, solid wastes, all these things, we combine them and we do an impact assessment relating to the inventory analysis that we made. Finally, we put all these results in front of us and then we interpret them. How can I reduce my environmental impact for this product? What conclusions can I draw? What is my most critical stage in this particular production system? What kind of recommendations I can make? So the reason to carry a life cycle assessment might differ. You can use it for decision making, you can use it for communication, or you can use it to learn about your system. Decision making is, for example, when you are making a policy, or when you are going to purchase something. When you are going to change your process design or product design, you can actually look at your life cycle assessment and evaluate what are my critical stages. Is this a green alternative? Can I basically change my process or product to make it a better version of itself, a greener version of itself? The second reason why you would carry out a life cycle assessment is communication. Basically, you want to market your product. If you green it, green your product, you can market it more easily. You can market it as environmentally more friendly. You can also use this for benchmarking. For example, company A is producing this type of material with this type of emissions. I am doing it at this level, so I can improve myself or At least I'm at their level, or they are worse than me. So this is again kind of like marketing, but also for your own company's benefits to improve your process or product. And also for eco labels and product declarations, you can use LCA. The third option would be learning about your product, identifying the improvement opportunities, identifying the liability concerns, and selecting some performance indicators, or you can also do it for research purposes. So I'm so sorry, I never asked how much time do I have?
Actually, we will decide 1 hour is enough.
Okay. How much? What is the time? So how much do I left?
There is 24 minutes. You have 24.
Okay, so I actually have so many slides. I will try to talk a little bit fast. Okay.
Okay.
So let's do an example. Let's start with defining goal and scope. First of all, you need to study your goal. What is your intent, the intended application of the study? For what purpose you are going to do your LCA? For example, to identify major problems, or are you going to do it to select one of the options? And then you need to also think about your context, for whom and compared to what I am actually doing this LCA. And output is how am I going to communicate my results. The first thing you need to determine is your functional unit. Is it 1 meter cube of material? Is it 1 ton of material? Is it 1 package of material? For example, 1 bag of cement, or 10 kilos of cement, or 1 meter cube of cement. These are all different functional units. Then I need to define my system boundaries. The system boundaries can be conceptual, or they can be geographical. For example, I'm only going to work for Istanbul or Ankara, or you can do it for a time period. For example, I'm only going to do this for June or March. And types of impacts to consider, you should also think about that. And you also need to determine required level of detail. Once you are defining your functional unit, reference flow against which all others are related is basically your functional unit. Establish a common level of performance across the systems to be considered. So you cannot compare 1 meter cube of concrete with 1 package of cement. You cannot compare them. And to make things comparable, you need to determine what your functional unit is. And examples can vary. For example, you can think about what is the environmental impact of producing 1 light bulb? What is the environmental impact of producing 1 meter square of wallpaper or paint? And about newspapers, how many newspapers? 1 newspaper, or 2 newspapers, or 1 bread, or half a kilo of bread. So this actually becomes the most critical part to determine your functional unit. Then you need to define your boundaries. How far do we go? Are we going to start from atoms? Of course not. So, but there's no theoretical basis for exclusion. So you can go boundaries as far as you can, but often broken at environmental flows or economical flows of value. Generally includes only processes in direct contact with the product and raw materials entering that product. For example, think of oil use. And you can start with different things. Are you going to only look at combustion? So if you are thinking of electricity, you can consider conversion efficiency, transmission efficiency. Are you going to only look at extraction of oil? Are you going to look transportation of oil? Are you going to look at refining? Or are you going to use all of them and include them in your system? Then we are going to do an inventory analysis once we have our boundaries. You build a system model of the flows within your system. And basically system boundaries and flow types defined in goal scope. And you take these boundaries and check the inputs and outputs in further detail in this stage. in inventory analysis stage. It typically includes only environmentally relevant flows. For example, most of the time in life cycle assessment, you exclude waste heat, waste oxygen emissions, or water. Sometimes these are emitted because they are not included in impact categories, but actually they are very critical too for many reasons, which we will not discuss here. Then how do we do inventory analysis? We first start to catalog what activities to include. So we draw a flow chart. Then we start to collect data, and then we actually compute the flows per unit of analysis. And actually there are certain difficulties about allocation. So for example, I'm going to produce a pen, or I'm going to produce this beautiful teacup. And what happens is I use energy, right? But to produce energy, I burned a lot of coal. So how much of the coal will be coal's burnings, electricity emissions will be included in the production of teacup? So this is actually an allocation problem. So that can sometimes be challenging. And then flow charts actually help to identify the scope of the investigation and nature and amount of the data required, and to see the logical system boundaries. With the scope of the investigation, generally it dislocates critical processes and also identifies hidden flows. And when you think of logical system boundaries, because there is no rule to choose system boundaries, the theoretically analysis boundaries should include all resource extractions and environmental emissions related to a product. But practically, the boundaries of an analysis cannot capture the complete picture. I want to show you an example from 2005, International Aluminium Institute's example. So they actually define their goal and scope. The goal of this aluminum-based life cycle assessment is, the intended purpose of this is to accurately characterize resource consumption and significant environmental aspects associated with the worldwide production of primary aluminum. It reflects the fact that primary aluminum is globally traded commodity. So basically we take the whole world and we are looking for resource consumption and significant environmental aspects with production of primary aluminum. The collected data will serve as a credible basis for subsequent life cycle assessments of aluminum products. So I determine my goal and scope. Then I go to the inventory analysis stage. Here, I actually draw a flow chart of my primary aluminum production. I start with my raw materials, bauxite. Bauxite, probably you all know bauxite is a source of aluminum, limestone, kireç taşı, and also we use petcoke and pitch. And we know how much of, we also use caustic soda in this production. And we know how much material we put. And basically we know there are different transportations, there are different wastes, and eventually we have the anode production, then aluminum production, and they come together. We form an electrolysis, then we cast ingots, and our primary aluminum is ready. Actually, this is our flow chart. So here we actually see how much material we consume and overall our flow. We can summarize it very simply. Aluminum is extracted from bauxite as aluminum oxide. This oxide is then broken down through an electrolysis process into oxygen, emitted as carbon dioxide by reaction with carbon anode, and aluminum as liquid metal. Because we want aluminum, we don't want aluminum oxide. Bauxite neydi? Aluminum oksitti. So we want aluminum, not aluminum oxide. Then once we have our liquid metal, we cast it at ingot. Ingot böyle döküyorsunuz ya, hani şeyde oluyor, pig iron gibi. We cast into an ingot, and the usual form of suitable for külçe herhalde mi Türkçesi bilmiyorum. ingot of the usual form suitable for further publication. We have our primary aluminum and we use it for different processes. So this is our flow chart. And we need to collect now. We had our goal, we had our scope, we draw our system boundary, and now we need to collect data. This stage is the most time and effort intensive portion. And we need to check allocation procedures. Are we going to allocate the emissions according to economic value? Are we going to allocate them according to weight or whatever else you are thinking in your mind that is logical? So you need to determine on allocation procedures, and then, especially if you have multiple product flows, then you calculate the energy flows and resulting extractions and emissions from different fuels. You don't always have to use one type of fuel. You can use a wide range of fuels. And time comes for inventory analysis. So we start with data collection. We check our inflows, so material and energy. We check our outflows, primary products, other products, and releases to land, water, and air. Then we think about transportation. What type of transportation? Are we transporting with train or barge or trucks? And the distance. And now we need to take qualitative decisions. For example, am I going to include the whole world, or am I going to think only about Ankara? What is the time frame? Am I going to take only the summertime or only October 20, for example? So we need to actually give certain decisions to limit or not limit our life cycle assessment. Another important thing to remember is certain life cycle assessments are site specific. So for example, for company A, this is the result. For company B, this is the result. These are site specific results. And then you can average them for industry average. So these are different. And there are different types of data sources you can use. You can use scientific literature and published studies. You can use different databases available for a price. And you can check industry and government records. You can check private consultants or industry associations. Most of the time I use Ecoinvent. This is the one I use, but it is very expensive, to be honest. So I use Gabi to do life cycle assessment, but there are different software you can use. You can actually get Athena, you can get Bees from NIST, and you can also have AIO LCA. These are other options, but Ecoinvent is most popular one, to be honest. I prefer it for many reasons, but number one reason I prefer Ecoinvent is that you can go to Russia, you can go to China, and they also use Ecoinvent. So it makes your results more comparable. Then you need to calculate your inventory. Basically, you identify interconnection flows, you normalize your data, basically convert all absolute flows to a quantity relative to one outflow. And then you should always remember, you choose one functional unit. So you have to arrange everything according to how much material or energy I need to produce that particular functional unit of that product. And typically, you need to also normalize data because reference flow serves as your interconnection, whatever reference flow you choose. LCAs are typically linear, and choice of reference outflow is arbitrary, it's up to you. And then you calculate magnitude of interconnection flows. For a linear system, it's very solvable using linear algebra, so that's not difficult. Then you scale all flows relative to interconnection flows. What does this mean? Şöyle anlatayım. Siz bir kalem üretiyorsunuz. Bunun için 1 kilo plastik gerekiyor. Plastiği üretmek için ama sizin elinizde 1 ton plastik üretmenin verisi var. Bunu 1 kiloya scale ediyorsunuz. Ya da işte 1 metreküp plastik gidecek. 1 metreküpe 1 kiloyu çeviriyorsunuz. 1 kilo plastik şu kadar ağırlık eder. O zaman 1 metreküpü bu kadardır gibi çeviriyorsunuz kafanızda. Hepsini aynı reference flow'a uygun hale getiriyorsunuz. And then once everything is converted, you sum all equivalent flows. here is an example, a product, trash can. Okay, biz çöp tenekesi yapacağız. The flow is like this. Ingots came from plot A. In plant A. In plant A, I extract minerals. I turn it into metal and cast it into ingots. Külçeleri madeni çıkarıp dönüştürüyorum. In plant B, it delivers metal sheets to plant C. Külçeleri alıyorum. Ingots are melted and rolled into sheets. Külçeleri eritip yaprak yapıyorum, sheet yapıyorum. Ve bunu C'ye veriyorum. In plant C, product P is produced. Metal sheets are cut and pressed to make product P. So let's go through this system. Okay? Bunu örnek olarak yapalım. And there are certain things that you should keep in mind. There are certain things that you should keep in mind. First, look at production details. I first check transportation. From plant A to B, it's 1,000 kilometers by truck. Plant B and C are adjacent, so 0 kilometers. Then I check the scrap. And processed scrap from plant C is returned to plant B for remelting. So scraps are remelted in plant B. And then let's look at product P. Product P weighs 40 grams and 60 meters square metal sheet needed to make 1,000 of these product P's. Metal thickness is 1 millimeter. Metal density is 8 tons per meter cube. So this is our general information. So we need 6 meters square to produce 1,000 product P's. And sheets are 1 millimeter thick and density is 8 tons per kilogram per meter cube. So to check this, let's check this out. First, let's check what happens in plant A, I'm sorry. The product of plant B is metal ingots. A raw material is the mineral. So let's write inputs and outputs down. The annual production is 1,200 tons per year. And basically, what do we use? We use 4,800 tons of raw material per year. And we use 6 million megajoules per year, the oil consumption. Emissions to air is 600 kilos per year. And emissions to water, 600 kilos per year again. And we have 3,800 tons of solid waste every year. So to produce 1,200 tons of ingots, metal ingots, product A basically, we actually have all these inputs and outputs. Let's check plant B. In plant B, we produce metal sheets. Raw material are the ingots coming from plant A, and we actually have some scrap metals. So total annual production is 1,600 tons of sheet. And we use 900 tons of ingots, 700 tons of scrap, and we use 5.6 times e to the 5 kilowatt hour energy for heating, and 3.26 e to the 5 kilowatt hour for rolling the sheets. And we also have 480 kilogram emission to air as hydrocarbons. And the plant C produces, actually buraya yanlış yazmışım, product is consumer product P, raw material metal sheets olacak, yanlış yazmışım. Basically, we produce 400 tons of product P, we use 408 tons of sheet, we use 3 e to the 5 megajoule oil, we use 2.22 e to the 5 kilowatt hour electricity, we have 250 kilogram emissions to air, and we have 80 tons of scrap, which is used in recycling. And we also need to, once we have all material flows now, we need to also look at the transportation and energy production emissions. Long haul and city traffic are two different things. For long haul, we use 1 megajoule per ton kilometer, and for city traffic, we use 2.7 megajoule per ton kilometers. And the energy production emissions are also important. So for each megajoule of fuel consumed, we produce different amounts of hydrocarbons, NOx, and carbon dioxide for oil and diesel, which are listed here. So this is the rough system. We have our metal ingot production at plant A. Things are transported into plant B to sheet production, and this will be used in plant C, which is basically product P production. So what you need to do is identify interconnection flows, then normalize the data, convert all absolute flows to quantify relative to one outflow. Typically reference flow serves as interconnection. Bunları hep söyledim zaten. Calculate magnitude of interconnection flows, scale all flows. So this is, then eventually you will sum everything up. So this is what you need to do. So once I do this, this is what I get. So for each functional unit, these are our outputs. For plant A, I produce hydrochloric acid and copper and some solid waste. And for plant B, şimdi C ile B'yi ayırmıyorsunuz ama ilki B, ikincisi C, renkleri aynı olmuş burada. Özür dilerim onun için, gözükmüyordur muhtemelen. So you can see in transportation, we produce hydrocarbons, NOx, and carbon dioxide. In plant B and C, again, we produce hydrocarbons, NOx, and carbon dioxide. So these are our outputs. And this is the energy part. So we use oil, diesel, and electricity in different stages. So overall, we use 230 megajoule oil, 40 megajoule diesel, and 49 kilowatt hour electricity to produce product P, to produce one product P. If electricity generation is 50% oil, 50% diesel, şimdi electricity dediğimizin de nasıl ürettiğinizi düşünmeniz lazım. Elektriği isterseniz hidroelektrikten üretin, isterseniz güneşten. Let's assume in this case 50% oil, 50% diesel, then 24.5 kilowatt hour from oil, 24.5 kilowatt hour from diesel. Şimdi burada unutmayın, elektrik kilowatt saat cinsinden ama diğerleri benzin olarak yakıt yaptığınız dizel ya da transportation, onlar megajoule cinsinden. Yani bunların birimi, functionality aynı değil. Bunları convert etmeniz lazım. So you convert 1 kilowatt hour is approximately speaking 3.6 megajoule. Although we are consuming 49 kilowatt hour of energy, 50% oil, 50% diesel, we are not consuming 49 kilowatt hour times 3.6 megajoule. 176 megajoule of energy carries. Why? Neden? Şimdi biz elektrik ile yakıtları yaktığımız zaman elde ettiğimiz enerji arasında bir fark olduğunu görüyoruz. Yani sizin 49 kilowatt saatiniz, eğer bunu megajoule'e çevirirseniz aynı performansı vermiyor. Yani 176 megajoule'lük enerjiden siz 49 kilowattlık enerji elde edemiyorsunuz. Why? Because energy conversion to electricity is far from 100% efficient. So you always need to have something called conversion factor. So here is an example. This is megajoule in, megajoule out for conversion efficiency. Şimdi coal thermal power plants, they work at 35% efficiency. Yani siz 100 megajoule enerji verirseniz 35 megajoule elektrik elde ediyorsunuz. Ha? Anlaşıldı mı burası? Biraz değişik bir şey oldu bu ama. And combined cycle and natural gas, roughly 40%. Fuel oil thermal, 32%. Diesel generation, 25%. Gas turbine, 27%. So do you know what is the efficiency of solar panels? Bilen var mı? So check it out. What is the efficiency of solar panels, okay? So then let's assume conversion efficiency for oil is 32 and for diesel 28, okay? O zaman biz bu electricity'yi bu conversion faktörleri de dahil ederek dağıtabiliriz artık. 1 kilowatt saat, 49 kilowatt saati. Buralara onu da dahil ederek dağıttık. Does this matter? So of course matters. So here we have the international, so basically the inventory for a ton of primary aluminum. We use coal, diesel, heavy oil, natural gas. So we know their usages, we know their energy content, and we know how much energy we consume. And we know our electricity. We consume around 15,711 kilowatt hour if you calculate it. If you exclude efficiency, then you will say, oh, this is actually 56,560 megajoule. But if you include the efficiency, it is actually 171,000, almost 171,000 megajoules. So total, if you exclude electricity efficiency, it is around 86,000. If you include efficiency conversions, then it is around 200,000 megajoules. So ignoring efficiency of electrical conversion drastically alters energy picture. Okay, so this was the basics for inventory analysis. Now you need to also consider something more, the allocation. Bu allocation sıkıntılı olabiliyor biraz. Consider adding two elements to scope of the analysis, use and disposal. Okay, here we added use of product P and end of life of product P. Here, this is the use. So product is basically your raw material is your product P. You use it, and then your output is your end of life products of product P. And you then go to disposal to landfill. Raw material is your end of life of your product P, and you will produce methane. So here we have total annual methane for a landfill. Şimdi landfill'den çıkan şey methane olduğunu biliyorsun. Total annual methane, you have your use of raw materials and emissions to you. This is your inputs and outputs for this particular system. 118.000 ton malzeme kullanıyoruz. 93 ton annual methane çıkıyor açığa. Ama bu yanıltıcı. Actually, this is misleading because how much of this should be allocated to metals? Şimdi siz bunu bir metal parçasını bir landfill'e gönderdiniz. Bu landfill'in içerisinde diyorsunuz ki benim landfill'im bir landfill'de işte yılda 93 ton metan gazı çıkarıyor. Ama sizin atığınızın içerisinde kağıt var, bahçe atığı var, çelik var, cam var, ahşap var. Biraz da bizim bu product P yani alüminyumdan olan olsun. Hangisi hangisinden geliyor? Hangi atık hangisinden geliyor? Bunu bilmiyorsunuz. Yani landfill'in bütün atığını bizim alüminyum şeylere assign edemezsiniz. Bunu bölmeniz ve dağıtmanız lazım uygun şekilde. Nasıl yapacaksınız bunu? Let's check the overall basically emissions of metal wastes. And bunu bizim ürün ne kadar aslında gerçekte yapıyor? Alüminyum metan açığa çıkarır mı? Bunu bir araştırmanız lazım. Eğer çıkarmıyorsa bu landfill'den açığa çıkan metan benimle bir alakası yok ki bunun. O başka bahçe atığından çıkıyormuş diyebilmelisiniz. Yani tutup ben bunu landfill'e koydum, landfill'in atığı da budur derseniz siz alüminyum üretimine metan gazını bağlamış oluyorsunuz. The inventory allocation basically is partitioning the input or output flows of a unit process to the product system under focus. It emerges when a process within our product system is associated with a flow that is part of another life cycle actually. It can be multi-outflow or multi-inflow. Avoiding problem by expanding scope of analysis to include other flows is an option, more applicable to change-oriented analysis, or you can partition it. Basically, if you check other flows and that are more accounting oriented, then you can prefer partitioning. Of course, partitioning is a little bit easier. Here is an example. Bir örnek size paylaşmak istiyorum. We have ingot casting. Elektroliz yapıyorduk bu ingotların, özür diliyorum. Anodlarımız, alüminyum oksitlerimiz vardı. Elektrik geliyordu, elektroliz yapıyorduk ve ingot, külçe üretiyorduk. Bu bizim şu ana kadar konuştuğumuz plant A. Plant A'de we actually emit carbon dioxide. Also we emit heat. Bir de waste ısı var, her ne kadar genelde dahil edilmesi de. Bu waste ısıyı biz kasabadaki, şehirdeki evlerin, binaların ısıtısında kullanalım. Atık ısıyı. Yani bizim plant A'mizden çıkan atık ısıyla etraftaki evleri ısıtalım. Sistem bu. Ve functional unity'miz de şu: 1 milyon ton aluminium ingot and 1 year of building heat. These are two different flows and two different functional units. 1 million ton of aluminum ingot and 1 year of building heat. So how are we going to combine this? There are two options. Check option A. Option A, you actually include everything and you basically expand your system to include all of these flows. The second option is basically separate these flows and assign all the heat, assign no heat actually, no heat. So waste heat is not even considered in the second option. Option A'de bütün hepsini toplu al. Option B'de ikisini komple ayrı al. At first, the system expansion seems greatly increase the scale of the analysis. Çok iş gibi duruyor. In fact, much of the implied expanded analysis can be excluded in a comparative analysis. For example, a change-oriented assessment. In practice, scope should include activities required for credibility, and you have to be careful that activities are the same in different scenarios. And then you can also do partitioning. Here, there are some technical causality. You have to establish relationship between magnitude of specific flows. So science-based assessment of landfill emissions, for example. And usually requires treatment of intra-process flows to a great level of detail. For example, energy used only for hydrochloric production in chloralkalies. Ya da physical quantity yapabilirsiniz. Yani ağırlıkça, mass, volume, area, energy content, moles. I produce this kilos of this product A, this much kilo of product B, so that's how I will allocate my emissions. Or you can do social causality, or you can just arbitrarily come something from your mind and I say 50-50. I divide all the emissions according to these between these two processes. The final stage is your impact assessment. Before interpretation. Interpretation'a hiç girmeyeceğiz. What is impact assessment? Basically, you attempt to describe the environmental consequences of the activity being studied. Basically, you have all these emissions, but you need to convert them into impacts so that everyone will be able to communicate. It reduces the number of data points against which you need to look at for decision making. And also, it adds information. It provides input from a range of scientists and other stakeholders. For example, when we say global warming potential, we don't say carbon dioxide. We actually look at carbon dioxide equivalent. So we actually add methane and other gases into that. So it's not just carbon dioxide when we calculate global warming potential. What is impact assessment? Impact category definition. Basically, there are different impact categories. These identify what impacts are of concern and which models will be used to translate inventory to impact. Then we do classification. Environmental stressors are correlated with specific impact categories. We go to characterization. Basically, we quantify amount of impact and we do damage assessment. Basically, aggregate the similar type of impacts. We do normalization and we do valuation. Valuation is possibly weighing impacts to rank or aggregate. Hangisi daha kritik bu çalışma için? Pardon, bu life cycle için gibi. Here there are two issues. The first issue is relevance. When you translate from inventory to impact, it introduces numerous assumptions and it can be sometimes controversial and its necessity depends on context. For example, expertise influence of decision makers may influence the extent of aggregation required. And ISO excludes weighing evaluation from comparisons for external distribution. And the second issue is translating environmental impact. The impact of pollution is rarely a simple one. For example, when you think of carbon dioxide, it increases thermal absorption, so raises temperature, but so what? And increased temperature means global warming. So assessment method must take into account causal chain, or you can exclude that. So this is pretty much, sorry, I forgot, there is a third issue I wanted to talk about. What effects to track? Basically, three broad categories of concern are resource use, human health, and ecological consequence. There is a debate over whether to include damage to the man-made environment. For example, acid rain damage to ancient structure. Böyle şeyleri de katacak mıyız? What about aesthetics and comfort? Are we going to include them? Key issue that you should always remember is double counting. Boundary between impact categories can be fuzzy. For example, oil depletion versus emission from oil use. So which one am I going to include my flow? Bunları impact'inde hangisine katacağını düşünmen gerekiyor. There are many impact categories with different approaches. Here, let me talk about some of them. Nordic guidelines talk about resource depletion, human health, and ecological, so three categories. In resource depletion, we talk about energy, material, water, and land use. In human health, we talk about toxicological, non-toxicological, or work and living environment. And in ecological, we have global warming, photochemical oxidation, acidification, ozone depletion, eutrophication, ecotoxicity, and biodiversity. When you think of environmental priorities system, first thing is human health, then biological diversity. We have then ecosystem production capacity, abiotic resources, and cultural and recreational value. When you look at classification of categories, actually, each of them is different. We have abiotic depletion, basically result of extraction of non-renewable raw materials. We have energy depletion. We have global warming, effects of carbon dioxide and other greenhouse gases such as methane. We have photochemical oxidant creation, smog. We have acidification, results of nitrogen and sulfur oxide releases into atmosphere. We have human toxicity. We have ecotoxicity, either to water or to land or to air sometimes. And we have nitrification, addition of nutrients to oil and water, resulting in reduction of oxygen. And we have ozone depletion. So inventory data inputs and outputs assigned to relevant impact categories. Hangi sistemi seçiyorsanız onun impact kategorisine sizin outputlarınız dahil ediliyor. And characterization basically is components of each impact category are aggregated to one representative type. For example, acidification potential is unequally affected by NOx, ammonia, and SO2. So when you're thinking about AP index, it is represented in kilogram of SO2. Şimdi normalde acidification potential'ına baktığınızda unit'i bunun kilogram SO2. Ama bunun içerisinde bir kere SO2 var. Sonra NOx'ları 0.7 ile çarparak, NH3'leri ise 1.9 ile çarparak yine bu acidification potential'ın içine ekliyoruz. Yani aslında impact kategoriler birçok farklı emission'ı toplayıp elde ediliyor. Okay, I think this is enough for today as a start to life cycle assessment. And I am sure there is so much more to talk. And I am sure you have some questions. Süremi açtın mı?
A little bit, but
sorry, I'm sorry for that. I know I would actually, but I didn't want to stop.
It's not so important. Thank you for valuable presentation, first of all. Then if you have a question about the presentation, you can write me via chat or raise your hand and ask your question to Çağla Hoca. Anybody ask a question?
I am open to questions. Anyone who is interested in impact assessment, please. I'm sure this seems easy, but actually it is not. It is like accounting.
There is no question in...
No question.
Hocam, actually,
I cannot
but all
believe that.
like all the time in the seminars, I'm the one who's asking the question, and I'm a little bit ashamed of it. So for just now, I'm not talking.
Okay, no worries. It's okay. And I'm sure some of you eventually will work on life cycle assessment. Please note that sustainability should always be a criteria for us. We are changing, world is changing, and hopefully most of you will work abroad or in Turkey. In your professional life, hopefully you will see a lot of sustainable solutions. And before, maybe 20 years ago, when I was at your age, actually, people did not have that concept. When I first come to METÜ after doing my PhD, I asked at that time, the department head, hey, my professor will visit. I want to do a seminar. He wants to give a seminar on sustainable concrete. And they asked me to translate it to Turkish. So I translated it to Turkish, sürdürülebilir beton. They all laughed. Sürdürülebilir beton because it sounded funny at that time. So this happened like 10 years ago at most. Ben 10 yıldır ODTÜ'de yokum. So it is not even 10 years ago. So things are changing at a rapid pace. People started to see the importance of sustainability only recently. Do you know Elon Musk, right? Everyone knows Elon Musk these days. He said, oh, Bitcoin is not energy efficient, so let's switch to a different digital coin, right? Because Bitcoin uses so much energy to produce Bitcoin. It's a simple thing, but it actually changed the whole industry a little bit. If any of you have any Bitcoin, time to switch to a greener alternative. So in every aspect, for example, if you are living in a building, especially with the climate change that is to need air conditioner more and more often. So if you had a building that actually has higher performing walls and windows, then you would not open your air conditioner, and you will actually save significant amount of fuel. And a very simple thing, you don't need to do anything. You just need to buy an eco window, and that would be your solution. It's a passive thing that you will do, but your behavior change, which means you prefer an eco product over a regular product, will have a significant influence on overall performance. The small things add up very quickly. You will choose the eco window, another person will choose another eco window, then companies will start to produce more and more eco windows instead of regular cheaper ones. So what you demand is what you get. Basically, if you look for sustainable solutions and push the industry towards sustainable solutions, either as a human being or as a civil engineer, basically you will help the environment slowly but surely. So that's all I want to say, I guess. Sorunuz yoksa, if you have no other questions.
I cannot see the question in chat box, and there is no hand.
Okay.
Okay. I will now leave the floor to the president of the civil engineering sustainability team, Sena Melis Kaleli, to give her special thanks to our teacher.
Hi, Çağla hocam. Such an insightful presentation. I just wanted to thank you on behalf of the whole team. And at the same time, I want to thanks very much to the project and seminar team. They are the ones who is organizing these events. But okay, can you see Çağla hoca, guys? Maybe is it me?
Yeah, we can see.
Oh, okay. And also our head of design, and also at the same time vice president of the social media and design team. She sorry for that. She just made this. You cannot see it, right?
Just before I can
no.
see. Huh.
Oh, okay. Maybe
No, we can see. We wait. Okay, we can see.
she just prepared this for you. We are appreciating
Thank you so
all
much.
of your effort, hocam. Not just this seminar and webinar series, but all your support, for your all
Thank you
support.
so much. Oh, that's so nice of you. Yeah, you might my environment day.
Yeah, oh, yeah. Also,
Thank you.
thanks a lot again.
Okay. I'm also thank you on behalf of ISS for taking time to give us this beautiful presentation and for answering our question. But there is no question. Doesn't matter. Maybe we will come together after a time, and we will make again a webinar, and maybe we can make a project in our campus. We will see. Thank you everyone for attending the webinar. See you in the next webinars.
Bir dakika.
Ha,
Bir
okay,
fotoğraf
Beyza.
çekilebilir miyiz? Müsait olanlarınız kameralarını da açabilirse çok güzel olur. Hazır şey yapıyorken, çekiliyorken herkes gözüksün mümkün olduğunca. Evet, çıkıyorlar. O zaman çekerim ben hazırsanız. 3, 2, 1. Çok teşekkür ediyorum hocam.
Thank you, Beyza. Okay, we will see in the next webinars. Thank you, everybody, everyone. See you later.
Bye bye.